Welcome to this explainer on the invisible engine, harnessing wind power for the grid. We see them all the time, dotting coastlines and rolling across hillsides, right? But beneath that elegant, slow-spinning exterior of a wind turbine lies a massive, invisible engine. It is an absolutely incredible feat of modern engineering that's fundamentally changing how we power our world. Today, we're going to unpack exactly how these towering giants capture the wind and, actually transform it into the electricity that powers our daily lives. Let's dive in. So, what happens when you run a fan in reverse? Let's start with a simple flip in perspective here. Think about an electric fan in your house. It uses electricity to spin its blades and create wind, right? Well, a wind turbine does the exact opposite. Literally, it uses the wind to spin its blades and create electricity. By harvesting the indirect solar energy that causes atmospheric winds in the first place, the turbine's rotor drives a generator to produce power for the grid. Now, to really grasp how they do this, we have to look at the sheer, staggering scale of these things. Notice that tiny white speck right at the base? Yeah, that's a full-sized utility van. These towers routinely reach 115 meters high, and the rotors span a massive 150 meters across. And this height, it isn't just for show. It is a strict engineering necessity. By towering way up over the landscape, turbines can access the faster, smoother, and way more consistent winds required to maximize their power output. Here are the 3 steps we'll be looking at today. 1. Kinetic energy from moving air. 2. Mechanical energy via the rotor and gears. And 3. Electrical energy from the generator. Getting that high-altitude breeze all the way onto the power grid relies on this 3-step journey. First up is kinetic energy, which is just the physical force of moving air. Second, that air pushes the blades, converting the kinetic energy into mechanical energy through the spinning rotor and gears. And finally, that mechanical motion is converted into electrical energy by a generator. Looking at this flowchart, you can see that exact transformation of energy. As wind flows past the turbine, it transfers a portion of its kinetic energy directly into the mechanical rotation of the machine. Honestly, the turbine is essentially a highly specialized middleman. But to snatch that energy literally right out of thin air, it relies heavily on aircraft science. Aerodynamics, lift over drag. Turbine blades are meticulously shaped with an airfoil design. They're literally just like airplane wings. As wind flows across the blade, air pressure on one side actually decreases, and this pressure difference creates 2 aerodynamic forces, lift and drag. They're designed so that the lift significantly overpowers the drag, and this forceful lift is what pulls the blades around, initiating that heavy rotation of the rotor. Now, for pitch regulation, which is the twisting of turbine blades around their own axes to the optimum angle, because, wind speeds fluctuate dramatically, modern turbines use this pitch regulation to adapt on the fly. A pitching device inside the hub intelligently twists those massive blades around their own axes. This adjusts them to the absolute optimum angle to capture maximum energy during a normal breeze, or, crucially, it stalls them to shed that aerodynamic force and protect the turbine during dangerously high winds. Directly behind those spinning blades sits the nacelle. This right here is the true powerhouse of the wind turbine. Think of it this way. If the blades are the hands catching the wind, this rectangular housing at the very top of the tower is the brain and the muscle. It does all the heavy lifting to prepare that raw mechanical energy for the electrical grid. Inside the nacelle, we have the drivetrain, gearbox, generator, yaw system, and the control and braking systems. It is incredibly densely packed with sophisticated machinery. But the really cool part is the yaw system. It uses a little anemometer to measure wind direction and physically rotates the entire nacelle to face the prevailing wind. Add in hydraulic cooling and heavy-duty braking systems, and you basically have a highly autonomous, flying factory suspended in the sky. The gearbox is all about multiplying speed, taking it from a slow 18 RPM to a blistering 1800 RPM. This is absolutely critical. See, those massive blades actually rotate quite slowly, usually just between 18 and 25 revolutions per minute. That slow, high torque turn simply isn't fast enough to generate electricity efficiently. So the gearbox uses a series of gears to multiply that rotational speed by a factor of up to 100, accelerating the output shaft to that blistering 1800 RPM. And here on this schematic, you can see the drivetrain connecting the gearbox directly to the induction generator. This is the final mechanical to electrical handoff. That high-speed shaft coming out of the gearbox connects directly into an induction or synchronous generator. Spinning at 1800 RPM, the generator uses electromagnetic induction to convert the mechanical motion into alternating current, or AC electricity. the physics of the wind has officially become usable power. For transformer and transmission, we are stepping up the voltage to 150 to 800 kilovolts. Why? Well, to send this power over long distances without losing a bunch of energy to heat and resistance, the voltage has to be stepped up. The electricity travels all the way down heavy cables inside the tower to a transformer, which steps it up to a massive 150 to 800 kilovolts. Once it hits this ultra-high voltage, it's finally ready to enter the broader power grid. 3.6. So what does all this incredible engineering actually yield? 3.6 megawatts. That is the staggering amount of power a single, average modern offshore wind turbine can generate. And by placing these massive generators in offshore locations where you have stronger, much more persistent winds, we are pushing that megawatt output higher and higher every year. 3.6 megawatts is enough to power roughly 3,300 average EU households. Just to put that massive number into perspective, think about that for a second. A single one of these machines, just quietly spinning out there in the ocean, can provide the total energy needs for an entire small town, literally turning thin air into localized, reliable power. So as turbines grow taller and technology advances, how will this invisible engine completely reshape the future of our power grid? We've seen how these incredible components extract energy from the sky, but honestly, we're only just beginning. As turbines grow taller, as carbon fiber makes the blades lighter, and as we get better at integrating smart energy storage, the potential is pretty much limitless. How will this invisible engine completely reshape the future of global power distribution? Well, that's the ultimate question we'll be watching unfold in the years to come. Thanks for checking out this explainer.